Hello. In the previous video, we found one kinematic model of a mobile robot. In this video, we will elaborate more on kinematic modeling and some of the basics about coordinate frames and transformation. So we will briefly define what kinematic modeling of a robot or a car is and what dynamic modeling is. We will learn a little bit about coordinate frames in 2D and how we transform coordinate frames to each other. We will see some different notations, and also I will explain a little bit more about that unicycle model that we talked about in the previous video. When modeling the motion of something, a car, a mobile robot, or anything, if you ignore the forces and moments and torques causing that motion, and you just focus on the motion and the velocities, position, accelerations, that would be kinematic modeling. If you include the forces and moments, then you are doing dynamic modeling. For cars, if they are moving in low speed, kinematic modeling works very well. Kinematic modeling is way easier than dynamic modeling. So if your car is moving at a very low speed, for example, mobile robots are usually moving at lower speeds, then kinematic modeling is more than enough. However, if you want your model to be valid in a higher operating range, in a wider operating range, you need to use dynamic models. It's more involved, it's more complicated. We will get to it in the next videos. Before talking about the kinematic model of a mobile robot, I want to tell you some of the basics of coordinate frames. There are three main sets of coordinate frames that we used in autonomous vehicle technology. One is inertial frame, also known as global frame or world frame. This is the only fixed frame we have. This is one fixed frame we put somewhere on Earth, and we calculate or measure everything else with respect to this fixed frame. We call this inertial frame. The second frame is a body frame. We attach this frame to one important part in the car, usually that center of gravity. This frame is not fixed. This is moving. As the car moves and turns, the frame, the body frame, changes too. Also, we have sensor frames. To each of the sensors, we attach a coordinate frame. Why? Because each sensor can measure things based on its own frame. Then we need to transform that measurement to body frame and inertial frame. So we need to be able to convert or transform what we measure in one frame to another frame. In a car, we might have many frames, so we need to be able to convert our measurements in one frame to another frame. So let's quickly review how we did this when we have several frames. Look at here, for example. We have a vector v, it can be the velocity of the car, and we have two coordinate frames. E, which can be, for example, the inertial frame, and B, which can be the body frame. So what we need to do is we must be able to describe the velocity v with respect to both of these frames. How are these frames transformed to each other? You can see here the origins in this example are the same. However, the body frame is rotated by theta degrees. The matrix which gives this transformation in some textbooks, in some sources, are described by this rotation matrix RBE, which shows body frame with respect to inertial frame. In some textbooks or some papers, they use this notation CBE. So I included both notations. In this course, I will stick to this notation, but for those of you who are familiar with this notation, here I mentioned the relationship to tell you what they are. So this rotation is given by this matrix. If your theta is, for example, 30 degrees, just replace that theta with 30 degrees. And the opposite rotation matrix, E in B, this is the matrix which describes the inertial frame with respect to the body frame, or we show it with CEB, is given by this matrix. It's actually a rotation by minus theta degrees. Let's see another example. Here something is a little bit different. This body frame compared to the inertial frame is not only rotated but also translated. And this is the vector, this O sub BE shows this translation of the origin from inertial frame to the body frame. So what are we going to do here? We assume that we know P, this point P, with respect to the body frame. We want to know, well, what is P with respect to the inertial frame? We have this value. We know where P is in B frame. We want to know where it is in E frame. In order to do that, we need two pieces of information. One is the translation vector. We should know how much the origin has moved between the two frames. One is the rotation matrix. We want to know how much the second frame has rotated with respect to the first frame. Having these two pieces of information, we can find P with respect to the frame E. We can know where P is with respect to the frame E. And this is the equation. This rotation matrix, we saw it in the previous slide. It's that cosine minus sine, sine, cosine. Then you multiply it by the position of this point in frame B. So you have this multiplication. Then you add this value, this vector, and you will be able to get the position of P with respect to E. You are going to solve examples on this in the quiz. I want to keep this video short, so there you will see the examples. If something is not clear, please ask me, I will explain more. Another notation for the same equation, for the same relationship, is this. So here E is used here instead of here. Instead of the rotation matrix RB in E, we use CBE of theta. Again, very similar. PB is the position of B, is the position of this point in frame B, and O sub BE is shown here. What if we want to do the other way? What if we know P in E and we want to find P in B? Very easily, the equation is given here. The only difference is instead of CBE, you should use CEB. And for example, the theta, if here theta was 30 degrees, here it would be minus 30 degrees. And the vector of translation is not O sub BE, it's O sub EB. Well, there is a problem with these equations, and that's we have a sum here. We usually, because we code all these equations, we like to have this in matrix forms so that we can multiply matrices and vectors. In order to do that, we are going to have a small modification. The modification is this. Instead of writing the position as x and y, we just add 1 at the bottom. So P has 3 elements. Why? Because then you can do this matrix multiplication. This whole thing here is a matrix. We have the rotation matrix, we have the translation vector, and then the sizes now match, and you can multiply this matrix and this vector. Here it has bar, so it's x of the point in frame B, y of that point in frame B, and then a 1 that we add. It gives us the position of that point in frame E. Previously, we talked about this mobile robot. We described a unicycle model to describe its motion. I want to mention a couple of more details about that model. One is that in the mobile robot and also in cars, we have a constraint which is named as non-holonomic constraint. In simple words, if I want to describe it in one sentence, that's it. the velocity of a robot or a car at any instance is tangent to the path. That's because how cars and mobile robots are made. If your car is facing this way, it cannot suddenly move in this direction. You cannot move in any direction where you are not pointing at. You can move in a direction where your wheels are pointing at. This is the non-holonomic constraint that we have in cars and mobile robots. So, in other words, your car can roll forward and turn while rolling. However, it cannot move sideways directly at any time. This constraint has effect on the model we find. So we have this relationship all the time. dy over dx, that's the velocity, equals tan of theta, as you can see here. And tan is sine over cosine, so you can write the non-holonomic constraint, which is given by this equation. If you look at the velocity component of the unicycle model we found in the previous video, you can see it was like this, and you can see it meets the non-holonomic constraint. You can double check that. So this is what we found previously. The inputs to the mobile robot was v and omega. This was the unicycle model, a simple kinematic model which described the motion of the mobile robot. And the states in this model are x, y, theta. All of you know what the states are. State is a set of parameters. We usually put them in a vector which fully described the current condition or state of any system. In this model, in this kinematic model, x, y, and theta, position and orientation, were considered as the state of the robot. I'm going to describe the unicycle model we talked about in the last session, but here the notation has changed a little bit. I did it on purpose because I don't want you to graduate and then when you start working, I don't know, in industry or academia, and then you see the notations are different. So I'm going to introduce a slightly different notation here in this video so that you are familiar with both. It's not a big deal. One difference is the distance between the wheels is described with 2L instead of one capital L that we had last session. This is nothing important. The other thing is something I mentioned previously. So in the unicycle model, the inputs are v and omega, but actually what we give to the mobile robot is the velocity of each of the wheels. In the previous video, we described them with VR and VL, if you remember. I just realized that there is some confusion there. VR and VL are actually phi dots. Phi means the angle of the wheel. It means it shows how fast the wheels are rotating. So I realized that you might assume that VR and VL are the linear velocity of the wheels. No, VR and VL are the phi dots. It shows how fast the angles of the wheels are changing. In other words, they are angular velocities. They are omegas. So I decided, in order to avoid that confusion, I will describe them with omega. So omega 1 is VR in the previous slide, and omega 2 is VL. The center is shown by P. L, small l, is the distance from the center to each of wheel. In the previous video, capital L was this 2L. Wheel radius is R, and wheel rotation rates. So this is what we called in the previous video with VR and VL, because in some textbooks that's how they are described. Here we show them with omega 1 and omega 2, and we have this relationship again in one of the quiz examples. I realized there is some confusion. We have this relationship between linear velocity and angular velocity of a wheel. If the linear velocity of the wheel is vi, so you can see vi here or here, then the angular velocity omega I, omega 1 or omega 2, is this. V equals R times omega. Now let's assume the linear velocity of a wheel is v1, the linear velocity of another wheel is v2, then the whole velocity of the robot is the average of V1 and V2. This is what you have seen before, the equation. However, the notations we used in the previous video was this. R half VR plus VL, if you remember. This is exactly this equation. This is the average of V1 and V2. Because V1 is R omega 1, V2 is R omega 2. If you factor R, you get the same thing. And have in mind, in the previous video, what we defined as VR is phi dot, which is omega 1. So this is the same equation. So if you see it differently in your projects or at work, know that these two are exactly the same thing. The same for the omega, the angular velocity of the robot. First, have in mind, if you consider V1 and V2 like this, then the ICR is instantaneous, center of rotation, and you can measure omega with respect to that. Previously, we saw that omega is R divided by L, VR minus VL. It's the same as this one. This is the same equation. So you can factor R, omega 1 is VR, omega 2 is VL, and capital L is 2L. So just be familiar with these different notations. They are the same thing. Let's summarize it. This is a continuous kinematic model of a mobile robot, the unicycle model. So I just replaced V and omega here. So x dot is V cosine of theta, and you can write V in terms of the velocity of the right wheel, the velocity of the left wheel. And finally, in practice, we usually don't use continuous time models because we are using microprocessors and everything will be sampled and discrete. We prefer a discrete time model. We will come back to discrete time models if you don't have the 487 digital control course. Don't worry, we will talk about it here. So this is a discrete time model. Instead of using the derivative of the states, instead of using x dot, y dot, we just define them as xk plus 1 minus xk. So at each instant k is instant. For example, at second 1, then at second 1.1, 1.2, so we keep going. We keep increasing k, so the time increases, but at discrete times, we have this relationship. And don't forget this delta t, which is our sampling time. That's it. Here you can see continuous time kinematic model of a mobile robot and a discrete time model. In this video, we talked about some of the basics of kinematic modeling. We saw coordinate frames and transformations. You will practice more this transformation in the quiz. And we saw continuous and discrete time unicycle kinematic model of a two-wheeled mobile robot. We will continue this discussion. We will start talking about the cars in the next video, and we move from unicycle model to a more complicated and precise model which describes the cars, and that's bicycle model. Thank you very much.